Good morning. Let me introduce our tool ObfusQate in this prestigious conference. Before we start, let me explain who we are. My name is Vivek. I am an associate professor in SIT. Along with me is Michael, who is my partner in this project. He is a CEO of Fraunhofer. Unfortunately, he is not here today. He has to fly to Germany for a family reason. And there are a few of my students here in the audience. They are as important as me, Nikhil and Malcolm. They have spent last 5-6 months helping us develop this tool. But not just them, there are a multiple number of students who worked on this project along with us, a research engineer. They all worked, they put their full effort, 100% of their efforts into this tool. So let us start the talk. Quantum physics has changed our world already. In the early 20th century, when the quantum physics came as a shocker to the scientific world, telling that locality is not the only way which things happen. Particles far away from the universe have some impact on us. Things can be in multiple states at the same time. So these are shockers not just for normal scientists, even people like Albert Einstein had a hard time believing some of the concepts that came from quantum physics. So things being a cat alive and dead at the same time is not something is acceptable for us human beings, right? But it is a reality and it has changed the world. We use quantum technology, quantum physics in many of our technologies right now. For instance, creating chips at the nanometer scale, using in MRIs and hospital devices, X-ray machines, etc. In telecommunications, in satellite communications, in GPS, all these places we use quantum physics, quantum mechanics. We need the properties of quantum particles to do those properly. And the final frontier on that is quantum computing, what you see over here. Right? So put some perspective on how it is different. The fastest supercomputer, El Capitan, can do 1.742 exaflops. That is like a million NVIDIA RTX 5080 working together. Okay? Or the latest NVIDIA DGX GB300 does 0.35 exaflops. This is equivalent to if you can compute one operation in a second, it takes 55 million years for you to do what El Capitan can do in 1 second. Right? If you take a quantum benchmark program, it takes a quadrillion years for the quantum benchmark problem to be solved in El Capitan. Okay? Compared to that, Google Quantum Willow does that in 5 seconds. Okay? However, this benchmark program is a dummy program. It has no major use. It's a very hard problem to solve, right? And a quantum computer can solve it, but it does not really solve anything important, right? People are looking at solving important problems, solutions which are important for the society that can be solved. So that comes in the right corner beyond classical applications. So that is where we are headed. Right? And a quantum computer looks something like this. Don't get scared of all this different this thing. The main quantum processor unit is a small chip at the bottom. And a quantum computing stack looks a bit like this. There's a quantum processor unit. And on top of the quantum processor unit, you have the quantum error corrections, controls, readout. And on top of that, there's a logical quantum processor, controls, readout, and quantum algorithms. So this is very similar to a classical computer architecture. You have the hardware beneath. Hardware is not stable. You need error correction mechanisms. With the error correction mechanisms, you have logical qubits. On top of logical qubits, you put your operating system. And on top of that, you have the quantum algorithms. Our tool ObfusQate comes at the topmost layer. At the ObfusQate comes here, the quantum algorithms layer. That is where we are trying to solve, safeguard your quantum algorithms with our tool. Okay? There are many quantum processors right now coming from Google, IBM, Microsoft, AWS, to name a few. But they're not just the players in it. You have PsiQuantum, SpinQ, Rigetti, etc. This is a quantum roadmap. We are at a stage where we are beyond classical. Until in 2019, it was called quantum supremacy. Google called it quantum supremacy, right? That quantum can do something much faster than the classical. They renamed it now. They call it beyond classical now. They say we are at milestone 2. We are at quantum error correction stage. The next will be building large, long-lived quantum qubits. And finally, the milestone 6 will be a proper quantum computer running properly all the algorithms that we want. Well, but what can we do with it in reality? Many things. Quantum simulation, optimization problems, complex systems modeling, like modeling prediction, predicting weather, modeling molecules, climate, etc. Search problems, pattern matching, database search, etc. Factoring for cybersecurity, factoring RSA, factoring problems, and future applications that we don't know. Yeah. So all these different areas, quantum simulation, the things that I just said, can be used in multiple domains: finance, cryptography, AI, space, energy, materials, biotechnology, microelectronics, robotics, etc. So it is something like a normal computing. You think of a normal computer. A computer is capable of solving problems, solving computations. But we use computers for AI. We use computers for solving multitude of problems in the society. The same thing happens with quantum. Once quantum computers become a full-blown reality, this can be used to solve the power that you attain with this quantum computer is enormous, that it can solve much harder problems much faster in different domains, right? But what are the estimates of the likelihood of this happening? People say different things. Microsoft says years and not decades. Microsoft, in their new platform that they created, they think it won't take years, it will be done in decades. Google says within 5 years. Within 5 years, large-scale quantum computers will be a reality, is what Google says. Amazon says up to 5 years. It take up to 5 years for it to happen. Continuum says by 2030. And we all know what NVIDIA says, it's for decades, 15 years, 20 years. But if you look at this, they are all not very sure when it happens. This could be like what the AI boom looked like in 2000s. People said ChatGPT or general intelligence is going to come in a few years. It didn't happen in a few years. It still haven't happened, but ChatGPT came 23 years later. So it could come in 2 years, it could come in 5 years, it could come in 20 years. But a good estimate from our perspective, from programmers, from security engineers, is to assume that it is going to happen, and it could be within a few years to a couple of decades, and start preparing for that. Right? The same thing, this you probably may not be able to read this, but US Department of Energy thinks the same. It can take, something will happen within the 5 years, but within 20 years, something significant will happen for sure. Having said that, how do we do practical quantum computing? These are the simple steps for practical quantum computing. Identify a classical problem and the complexity. So what is a problem that we have? So there's a factoring problem that we have. Right? So that is based, all our cryptographic measures, many of our cryptographic measures are based on factoring problem. You determine if this problem has a quantum advantage. Is there a way in which this can be solved in a much faster way in a quantum computer? Not everything can be solved with quantum computers. Not everything can be solved with a classical computer, right? So we need to see, just as programmers, we look at problems and see if there is a solution for this with a computer. If there's a solution for this with a computer, we use it. Similarly, we look at a classical problem and see if there's a way in which this can be mapped into a quantum problem. If yes, then we reformulate it into a classical quantum framework. design and implement the quantum enhanced algorithm, and deploy and execute. So this is essentially how it works. And the deployment and execution part, there are different platforms like Qiskit from IBM, Penny Lane, Kibo in Singapore. So many different middlewares are working on it to enable us to do this. Okay, let me show a simple example how easy it is. So you can see here over here, this is an intrusion detection problem, and you can see a classical Python code where we are using a logistic regression, right? So the code looks very easy because there are a lot of libraries nowadays. The quantum equivalent of that, the code looks like this. The yellow part over here, this is how the code looks like. So this is how easy it is to find a solution right now. So if you want to do something using QA/OA in quantum, there are libraries which will help you do it. This cannot run on a large intrusion detection problem because we don't have a large quantum computer to solve this. The algorithms are ready, right? So even though the computer, the hardware is not fully equipped, the algorithms are ready. People are working on algorithms at the same time. This is where ObfusQate comes in. We need to protect these algorithms. That is where ObfusQate comes in. So we can safely assume that the code is going to be run, in the short term at least, on somebody else's quantum computer. So at that point, security and trust becomes a factor. Data security, privacy, IP, know-how, digital trust, integrity, and reliability of the quantum code and data. We target IP and know-how protection. How can we protect the IP and know-how of your quantum algorithms? If you classify quantum algorithms into two separate classes, secure quantum computing programming and quantum data science, that is where most of the quantum efforts are going around nowadays. The intersection is where our tool comes in, IP and know-how protection. Okay, now I've set up some history over here. I need to do two aspects before I jump into ObfusQate and what we do in ObfusQate. Many of you may not be coming from a quantum computing background, so some basics, bare essentials, that helps you understand how the tool works. First is, what is different in a quantum computer? A basic unit of a quantum computer is a qubit. A basic unit of a classical computer is a bit, which can take 0 and 1 as input. A quantum bit is called a qubit. A qubit, just like classical bit, can take 0, can have a state of 0, can have a state of 1, and more excitingly, it can take the state which is both 0 and 1 at the same time. So it is not 0 or 1. I can put the qubit in a state where it is 0 and 1 at the same time. This is called a superposition state. Okay? The moment you look at it, it will collapse to one of the states. That's a different issue. But until you don't look at it, it will be in a flux. It will be both 0 and 1. So it acts as 0 and 1. So that is number one. Number two is quantum gates. Just like classical gates, like a NOT gate, which operates on classical bits, a quantum gate acts on a quantum bit. So if you give an X0 gate input as 0, it will convert the qubit state from 0 to 1. An H gate, for instance, if you give an input 0, it changes the input 0 to a state of superposition, which is 0 and 1. You see, the advantage of putting something in superposition is tremendous. If I can put 1 bit in a superposition of 0 and 1, I can put 4 bit in a superposition of 0 to 16, all possible values. So you're giving an input as, imagine you're trying a search problem. You're searching, instead of 1 by 1, you're searching all 16 at the same time. So that is the power of creating things putting things in a superposition state. Let us see how programming is different. In classical computing, an input to a square function is 2, the output is 4. In quantum computing, the input to the superposition, input can be 2, then the output will be 4. I can also put input in a superposition state of 2 and 4 and 5. If it is in a superposition state of 2, 4, and 5, the square function will operate on that superposition state, and the result will be in a superposition of 4, 16, and 25. Parallel computing without a parallel computer. So you are doing all, the operation, square operation takes the same time to operate even if the input is just in one state or in a superposition state. There is no more time complexity is the same. Just that the result of this is in a superposition state of all the answers. So this gives tremendous power to quantum computer compared to exponentially larger than that of a classical computing. Okay, so this is what people capitalize on. So the first thing I have, just to recap, we looked at what qubit is, we looked at what superposition is. Okay, I promise this is the last lesson on quantum computing that I'm going to give. One more property that we look at is entanglement. Okay, so two qubits are entangled means individually they are random. They're both in a random state. They're both can be 0 and 1. But when they're entangled, they both give highly correlated results. It's like two people who are walking towards each other. They are independent people, they have random choices. But somehow they are always making the same move. The classical example I always use is getting married. Until you marry, you have your own ways. Wife has, or your girlfriend has her own ways. Once you're married, there is no your way or your wife's way. It's only one way, right? Mostly it's wives, but yeah, that's the example that I always use in my class, right? So these two qubits are so entangled that if I put in a state 0, 0, and 1, 1, independently the qubit can be 0 and 1. So when you measure, it can be 50% probability of getting 0, 50% probability of getting 1. But if one qubit is 0, the other, no matter what, is going to be 0. Even if the other qubit is at the other end of the universe, it is going to be 0. So this is a property which is difficult to wrap your head around. Einstein spent like 30 years saying this is wrong. There is something more to quantum computing, quantum physics than this. But we are not Einstein, we are mere mortals. So we accept this like a religion and enjoy the benefits. So if one collapses to, if one of the qubits collapses to 1, the other collapses to 1 as well. Okay, now let us get into our meat. So what will quantum programming looks like if you're not a millionaire? If you're a millionaire, it's fine. You can buy a quantum computer and then you can start doing quantum programming. But if you're not a millionaire, the programmer will create a quantum algorithms. So quantum algorithms, remember, consist of gates, qubits. So you put qubits and gates together, you create the quantum circuit. Every program is at the end a circuit, right? You send this to a quantum computing cloud service. You can send it to IBM's Qiskit machine, or you can send it to Amazon's machine, or if you can send it to Google's machine, whichever machine is providing a quantum computer, you send this program to a third-party quantum computer computing service. It computes your algorithm, it computes your circuit, gets the results back to you. Just like how 1950s computing looked like. You punch cards, you take the punch cards, go to a computer company which has a computer, give the punch card, get the results, and come back. The problem with this is, what's the big idea here? So the problem here is, your algorithm, the quantum algorithm with all the power quantum computers have, is going to be a precious algorithm, right? You're going to solve problems. You're probably going to create a new molecule that can cure COVID or something, right? You're giving this algorithm to a third-party company which is very powerful and having a lot of resources. Right? They can say that they are not going to steal it. Who knows? Right? You need some protection for the IP that you created. So that is our idea where we are going to obfuscate, change the program in such a way that it is not easy to decipher the logic, but at the same time, the program's semantics, the meaning, is preserved. Okay? We all know what obfuscation is. So ObfusQate with a Q is an obfuscation tool for quantum programming, right? So quantum obfuscation framework, as far as we know, this is the first obfuscation framework for quantum programs. There are 8 in the initial version of this. We have given 8 different obfuscation techniques. 4 are at circuit level, 4 are at the code level. Why circuit level and code level? Because quantum program right now is at the nascent stage where many of the programs are written at the circuit level. So the circuits has to be protected. But at the same time, you can use mostly we use Python, but there are other languages that you can use. There are code as well. When you create the circuits are written in code. So there's a classical quantum coexistence at that point. Why don't we use quantum power to protect the code as well? So we have 2 classifications, circuit obfuscation and code obfuscation. We'll see each of it and what each of these techniques do. In circuit obfuscation, the basic idea is to modify the corner circuit, essentially add or delete gates from the quantum circuit without changing the meaning of the program, because the program semantics has to be preserved. Because if the program is supposed to do something, it has to do that, right? Just randomly adding and deleting circuit, things to circuit basically means everything get messed up. So you preserve the semantics. At the same time, it will be difficult to understand the logic. We'll see some examples to see why it is going to be difficult. The first technique is the simplest technique, is where we create an obfuscation using inverse gates. So an inverse gate is if the friend of my friend is enemy of my enemy is a friend. A friend of my friend is not an enemy. Yeah, sorry for that. But an enemy of my enemy is a friend. Okay, but sometimes a friend of my friend can also be an enemy. But yeah, so same concept here, right? You have an H gate. If you not something twice, in most cases, unless you're emphasizing a sentence, it is going to be true. Like I not something, 0 is not, it becomes 1. 1 is not, again it becomes 0 back, right? So you can negate that operation by just using the inverse of that. So that is exactly what we do here in inverse gate. We add some gates. We add an H gate, and then we put the inverse of an H gate, which is an H gate, right? We add a NOT gate, and we add an inverse of a NOT gate, which is a NOT gate. We put a T gate. We don't need to know what a T gate is, but if you add a T gate, you put an inverse of a T gate. That operation cancels itself out. But it makes the circuit more complex. So simple circuit like this on the over here, it will be completely changed into an obfuscated circuit like this. You can see the complexity of the circuit just expands. However, there's a problem with this. I mean, a simple script can find an H and H together, right? So we hear you. So to make it more difficult for people to remove this obfuscation, deobfuscate this, we use something called delayed gate obfuscation. In delayed gate obfuscation, it is similar to the inverse gate, but we delay in adding the inverse gate. We find a position in the circuit where we can put the inverse, the farthest we can, to add that delay gate, the inverse gate. So the operations cancels easily out. The meaning is preserved, but it is not as easy as just looking at is y followed by another y, or h followed by another h, right? So that is delayed gate obfuscation. The original circuit will be completely converted into an obfuscated circuit, as you've seen over here. So now, in the first 2 obfuscation, we are dealing with simple gates that is available in the quantum circuits. We wanted something more complex. So we created something called composite gate obfuscation. In composite gate obfuscation, we created larger reversible blocks. So you can see over here an auxiliary gate, and the reverse of it is called a restore gate. And they're not the same gates. The auxiliary gate is HH, ZX. The resistor for that will be X, ZX, ZHH. So these two gates combined together, it nullify everything. There is no operation going to happen. It is like an NOP operation, but they are not easily identifiable as gate and its inverse. So we create a set of auxiliary and restore gates to have a larger reversible blocks that we can insert into the circuit, right? So an example of a obfuscated circuit looks like this. We'll have auxiliary, restore, and all the other operations in between. The last of the circuit obfuscation is clocked gates. In clocked gates, we know that one gate can be represented using a combination of other gates. So instead of X, I can use either SYS, HZH, HYH, different combinations. So we change these gates in different equivalent combinations. Okay. Now, one thing you need to remember is that we can use all these obfuscations in tandem. We can use one obfuscation and iteratively we can use 1, 2, 3, 4. So the complexity just adds up and makes it more and more, messier. For instance, I can do inverse gates first, then do clock gates, then do delayed gates, etc. That's the first type of obfuscation. The second type of obfuscation is chord obfuscation, where we have 4 types. What we do over here is we modify the code by adding extra branches and adding junk bytes. But when you add junk bytes and extra branches, some of those branches shouldn't execute, right? So all these opaque predicates are shielded with a quantum challenge. So to deobfuscate this, you have to essentially solve a quantum challenge, right? So that is what we try here. In chord obfuscation, one obfuscation type is simple entanglement obfuscation. Remember the entanglement example that we said earlier, your wife and you only have one opinion? Same thing. If it is 0, 0 plus 1, 1, both qubits will end up as 0 or 1. But if you look at, you know it at the compile time, but an attacker reversing it does not know it, right? So we know that the branches 0, 0 and 1, 1 are the only branches that are going to execute. So that is where the legitimate code is going to be placed. In the other 2 branches, we can put whatever junk code we want. But an attacker doesn't know these are going to be branches that are not going to get executed. Because individually, these bits can be 1 and 0 at the same time, right? So this is a simple entanglement-based obfuscation. We have a variable qubit pairs obfuscation. In this case, we use entanglement, but in the previous example, we know there are 2 branches which will definitely get executed, the other 2 branches which will not get executed. In this case, we'll put a bit of randomness. We make sure that all the branches can execute. So the junk code branch can also execute, but with a very low probability. For instance, if you only use one pair, there's a 50-50 chance that both branches can execute, and 50% of the time you get the wrong code getting executed. But if you increase it at the 8th pair, the probability of those wrong branches getting executed comes down to 0.35%, which is very small. But essentially, that is also not correct, because if you're running your code, the code should always run the correct code. So we have a solution to this, which we haven't implemented, which is basically if that branch happens, then you add a reset function there to start the program once again. So once in 1,000 times when the wrong branch gets executed, it restarts the program. Okay, so this is probability-based obfuscation. So there are 2 techniques which are entanglement-based. There is 2 techniques which are superposition-based. In the superposition shroud, we keep the qubit in a state of superposition. We make sure that the qubit is both 0 and 1, which means q equal to 0 and q equal to 1 both are true, which means I can take the code, split them into half, and put it in 2 different branches. In a classical program, only one branch gets executed. In quantum, because there's both 0 and 1, both branches get executed, right? So I can take classical part of the program and put it in 2 different branches and make it work. And finally, the last is a branch obfuscation via superposition, where in the previous example of superposition, both branches execute. Here I'll keep 2 qubits in a superposition state, but at the compile time I know that only one of the state is going to be, it will only collapse to one of the state. Right? So we put junk code in all other states and run the true code in one of the branches, which is 1, 1. So these are the 4 different obfuscation techniques. So let us see all these things happen with the press of a button. So we can go to obfuscate.com. It's available online. It's very easy to implement. You run, go to obfuscate, gets, okay. So you go to obfuscate and go to circuit-based obfuscation. You have 4 of them. Each of them have some simple explanation of what really happens here. And press here. This is where you put your code. The input that we accept is OpenQASM 2.0 and OpenQASM 3.0. QASM is quantum assembly. We are in the process of migrating this to QAR also, so all the different standards. So right now these 2 standards are accepted. So you can put your code here. We have put a sample code here, but if you run quantum algorithm, just compile to OpenQASM and then put the code here, and press a button, obfuscate. Within seconds it will obfuscate. So we ran this code 1024 times. Every time the answer is supposed to be 1000 in the original code. Every time the obfuscated code also gave the answer 1000. Let us see how the circuit looks like. This is the original circuit. The original code looks something like this, and tada, the obfuscated circuit look this complex, right? So that is an obfuscated obfuscation. We have 4 different types of obfuscation in the circuit obfuscation. In the code obfuscation, let us take an example. Let us use this. It obfuscate, and again within a second you get the original code here, and you will get the obfuscated code on the right side. So you can see there are more branches added. If selected path is 0, 1, do certain things, else if selected path is 1, 1, do something. So this is essentially what it does. You can download the Python file from here. Obfuscated, the code will work perfectly. So we have all the 4 different type of obfuscations. Okay, so in a nutshell, we have obfuscate to protect your code before you sell it to a third party quantum computing provider. But that is a defensive use case. Every coin has 2 sides, right? I have a nice side and I have a bad side. So obfuscate also has a bad side. We can use it for offensive use cases as well. Let's say a quantum program, we can add malicious code into it. Right now it is more essential because more and more people are getting into quantum, and most of them uses GitHub based, because you need to start somewhere. So use code libraries that is available in GitHub. What if I add a malicious code into the quantum program? Let's say I add Shor's algorithm, which is an algorithm to factor your program, factor your numbers, which is mostly used for RSA cracking. Add a keylogger to it. Can reverse engineering tools or malwares, antivirus software is able to find this? Yes, they are. For a very simple task, we just gave it to a few LLMs, and they can immediately identify there's a quantum code and a malicious shell code embedded in that program. But what if we obfuscate it? What if we obfuscate it so that the malicious code is, completely obfuscated within the original quantum program. What will these LLMs give as an output? The output is not stunning, but it cannot identify the quantum code. At least with very simple prompts, it cannot. It identifies only the quantum code. It cannot identify the keylogger, right? Having said that, this is one of the, we did it a month back. We have not extensively trained the LLMs using quantum code and obfuscated code. So that is something that we are looking into. If you are in that space, please come to talk to us. We'll be very happy to hear your thoughts. But with initial, inputs, we always see that GPT-3 Mini, GPT-4, Grok 3, they all identify unobfuscated code with just one instruction. What does this program do? But not with the same instruction, it cannot find the malware in the obfuscated code. So that is mostly my talk. But what does this mean to you? The future of coding is going to be quantum and classical. Maybe 2 years, maybe 10 years, but it is coming. Many of you, maybe in your work, people are probably asking you to change code into PQC compliant. Quantum code is going to come, and you will be adding quantum features to your code base. At least in the near term, these code that you create run in a computer far, far away. At that time, if you care about your IP, I would say obfuscate. With that, I want to end the talk. You have all these things that we want to give you. We have if you want to use obfuscate.com, you can go to obfuscate.com, obfuscate your code with the press of a button. But I cannot ask you to trust us when I say that you cannot trust IBM. So if you don't want to put your code in obfuscate.com, we have a Docker version. You can download the code, put in your Docker, and use there. And there's a white paper. We have submitted it to a couple of one conference. So it is in archives. You can read more details on the technology and techniques that we have used in the white paper. Thank you.